Welcome back to Complex Analysis. So we're going to finish out the chapter with logarithms and complex exponentials. Now, just a quick review on logarithms back in pre-calculus. Logarithms were really made or defined as the inverse of an exponential function. So log base a was defined so that, again, it undoes what a to the x does, the exponential function. So logarithms are just inherently, they're built to be inverses. Just a quick example, let's say we were looking at log base 2, so our base is 2 of 8. Okay. Now, what does a log represent? Well, a log really represents what power do you need to make the base to get your input. Okay, so if we think about 8, well, 8 is 2 to the third, right? So we need to raise our base to 3, and that'll give us 8. So this outputs the number 3. So the log is really sort of, at least in a pre-calculus sense, it's the search for the power. What power do you need to make your base to get your input? Whereas the exponential function itself, if we had 2 and we plugged something into the power there, well, it's sort of a straightforward calculation, right? 2 to the 6 is 64, I believe. Okay. So inherently, logarithms have this like inverse quality about them, and that's what I think makes them a little bit more complicated. They're not as straightforward as, oh, you just plug and chug and you're good to go. No, when you try to compute a logarithm, you're really trying to search for that power. Another example, let's just say we're looking at log base 3 of, I don't know, 1 over 3. Okay. What would this be equal to? Well, this would be equal to -1, because how do you get 1/3 from 3? You have to raise 3 to -1. Okay. So again, it's that search for a power. Now, logarithms in a complex setting aren't this, I would say, straightforward. We're not looking for a power anymore because exponentials aren't really power functions anymore, because remember, they have sines and cosines in them. So it's a little bit more complex, but at least our motivation, though, is still to undo the complex exponential function. So we're sort of guided by that. When we're looking for a logarithm, okay, we're really just trying to undo the complex exponential function. Now, what we're going to see today is that logarithms are kind of like a family tree. That might sound weird, but logarithms, I'm going to write this down, a family tree. Because there's, in fact, infinitely many logarithm functions now. And they're a tree because we sort of treat them as sort of branches in a way, and that'll make, I think, a little bit more sense once we get further into this video. But think about logarithms as a tree. So really there's, well, here's the trunk, and then off the trunk here, I know this is going to look sort of strange, we have branches, right? Now you might be like, I've never seen a tree like this ever in my life. Well, that's true, because maybe you haven't actually seen a complex logarithm yet. But in any case, logarithms, I want you to think about family trees. There's infinitely many logarithms, and we're going to sort of think about them as branches, or we're going to take a branch of the family tree here, or the logarithm. Now that'll make a little bit more sense down the way, so keep that in the back of your heads, though. Just think family tree, family tree. Okay, so let's go and get started. All right, so again, our motivation for the logarithm isn't, again, it's not trying to undo the power in a way. It's actually trying to just undo the exponential function. So when we're talking about log, we're really trying to find a function that satisfies the following here. Okay, so if we have the exponential function composed with log, whatever this function is, we want to make sure that that's equal to log of the exponential function is equal to z. So basically, it's a function that's canceling out or undoing the exponential function. Okay, so in our search for a log function and how to define it, we're really guided by this principle right here. We want to find some function, which we're going to call log, just for namesake, that undoes the exponential function in this way right here. It cancels it out no matter which way you compose. And again, that should remind you of this is what inverses do, right? Inverses, no matter how you compose a function in its inverse, you cancel each other, or they cancel each other out, and you're just left with your input. So we're still guided by that principle when defining the logarithm. Now we have a little bit more complexity, though, in complex analysis, no pun intended there. But there's a little bit more complexity because, remember, the exponential function's not one-to-one anymore. Remember, it's periodic because the exponential function, exp of z, remember, we define that as e to the x times, cosine of y plus I sine of y. Okay. That's not a one-to-one function anymore, so we don't have an inverse like we or a straightforward inverse like we're used to, let's say in like pre-calculus or something. So we have to be a little bit more careful. Okay, now what we're going to do, if you guys remember back in pre-calculus, we're going to do a similar thing. Let's just go back in time for a second, and let's just think about sine. Okay, so now we're back in time. Back in time. So if we remember the sine function, sine of x, okay, sine of x is not one-to-one, right? If we draw the picture of sine, it looks like this. It's like super not one-to-one, right? And by the way, that's not a mathematically precise way of saying that. But in any case, it's super not one-to-one. If I draw a horizontal line, let's say here, it's going to intersect this graph infinitely many places, okay? So what did we have to do back in pre-calculus? Well, we had to be a little bit more creative. So what we had to do in pre-calculus is we had to chop up sine. We had to say, whoops. We had to say, well, I'm just only going to look at a certain portion of sine. Okay, and typically what mathematicians do is they look at sine between, they look at sine between negative pi over 2 and pi over 2. So if I take my sine function and I chop it up so that I only have the x values between negative pi over 2 and pi over 2, then I actually get a one-to-one function, and then we can use that to define arcsine or sine inverse. Okay, so that's what we did back in pre-calculus, or maybe, I don't know, trigonometry. Maybe in trigonometry. I don't remember if we actually taught that in trigonometry. I never took a trig class, so maybe I'm not the best person to be saying anything like this. But in any case, wherever you saw sine inverse, which I'm sure everyone has, and you should have seen sine inverse, this is how you have to define it. It's always kind of a little weird because you have to take sine, you have to butcher it, you have to chop it up, and then what's left over is what we sort of define our inverse trig function. So we're going to do a similar trick for the exponential function, or we have to, because again, the exponential function is not one-to-one. It was back in calculus because it just looked like this. That's definitely a one-to-one function. But in complex land, exponentials are not one-to-one, so we have to be a lot more careful. Okay, so definition. So given a region G, and this is where, again, that family tree is going to start to show up. So given a region G, okay, and remember, a region is just an open, it's an open set in C, or at least that's part of the definition. Given a region G, any continuous function, we're going to call it log with a fancy L, from G to C that satisfies our cancellation property here, x of log of z is equal to z, is called a branch of the logarithm. Okay, so again, a continuous function log. By the way, we're not actually defining anything. We're just saying if we have a function, okay, that satisfies this cancellation property and that's continuous on its domain, then we call that a branch of the logarithm. Okay, and like trees, there's lots of branches. In fact, there's infinitely many branches. Now, just to show you that we do actually have a branch of the logarithm, let's do a little bit of investigating. Okay, so let's suppose that log, which I don't even know what it is at this point, or we don't know what it is at this point, but let's suppose that we had a function that did this. Okay, so suppose there is a function, so there exists a log, okay, that satisfies exp of log of z is equal to z. Okay. Now what we're going to do is we're going to rewrite, so log is a function, right? And it's a complex function, so that means that log of z can be written as, and actually I'm going to change to red here so we can see this a little bit better. Okay, so we're assuming x, oh, that's much better. Okay, so in any case, again, log here is a complex exponential function, so we can always write it as its real part, which we'll call u of z plus I v of z. Okay, so hopefully everyone's okay with that. We have a complex function, okay, log, which again, we don't know what it is, but in any case, any complex function can be written in terms of its real part and its imaginary part. Okay, so substituting this into our equation here, we have exp of u of z plus I v of z is equal to z. And remember, what does the exponential function do? The exponential function does this. It takes the real part, puts it in the exponent of e, you know, the number e, the natural number e, and then essentially it multiplies it by e to the I of the imaginary part. Okay, and that's still equal to z. Okay, so hopefully that makes sense to everyone. That's just using our exponential function that we looked at last time. Okay, and that's what the exponential function does. E to the real part times e to the I times the imaginary part. Okay, now where is this getting us? Well, let's go ahead and rewrite. So again, remember we can think about complex numbers in a lot of different ways. Let's rewrite the complex number z as r e to the I phi. Okay, so then we have two equations here. Although it might not look like it at first, but we do. Okay, so this gives us two equations. Because if you think about the right-hand side, well, the only real part of the right-hand side is this right here. And then we have this imaginary bit right here. Okay, so what this gives us is two equations. We get that e u of z is equal to r. Okay, and two, we get that e to the I v of z is equal to e to the I phi. Okay, now one of these equations is great. One of these is, it's good, but it's not the best it can be because it's actually a little bit complicated. So let me rewrite these. So we have e to the u of z is equal to r. So taking the natural log of both sides, we get u of z is equal to ln of z, or ln of r. Now I pulled a little switcheroo on you. Remember, r really is the absolute value of z there. But I'm writing it in this way because that's eventually how we're going to write it. Okay? So that first equation that we just got tells us that the real part of the log, because remember the log we're writing as u of z plus I v of z, we know that the real part has to be ln, the ln that we know and love, of the absolute value of z. Okay. Now here's where things get a little bit more complicated though. Let's look at that second equation. So we had e to the I v of z, which was the imaginary part of our log function here. And we said that this was equal to e to the I phi. Okay. Now unfortunately this doesn't mean that v of z has to be equal to phi. Okay, that's just not true. Okay, what this implies instead is that v of z is equal to phi plus any multiple of 2 pi k, because remember these are angles, right? And different angles can lie on top of each other. So it doesn't mean that, for instance, think about like pi over 2, and I got to think about it, let's see, 3 pi over 2 and 5 pi over 2. Okay, those angles are lying on the same place, right? They're lying, if we draw them, they're lying right here. Okay, but they're not the same angle. So that's what this equation is saying though. It's saying that we have the same angle, or we have an angle that lies on the same place, but they don't have to be the same thing. But at least we know that they have to be a multiple of 2 pi off. So for instance, pi over 2 and 5 pi over 2, well, 5 pi over 2 is equal to pi over 2 plus 2 pi. Okay, so at worst, we're off by a multiple of 2 pi. So that's what our equation is saying here. Okay, so our log function is really ln of z plus I times some angle function. Angle, for lack of a better word, I'm going to put angle function here. Okay. So in any case, we've sort of characterized in a way what the logarithm should look like. The logarithm has to either look like ln of z, but we have a little bit of freedom here in this angle function. We actually have a lot of things that this could be. Okay. So what do we usually take it to be? So this is what we call the principal logarithm. So usually in class when we talk about logs and we don't say anything, this is the log that we're really thinking about. So let arg of z, so we're defining a new function, let arg of z denote the unique argument of z not equal to 0 that lies in negative pi to pi. So let me draw this for you really quick. Okay. All right, and here's the positive real axis. So in any case, we're talking about angles that lie in between minus pi, but not including. So that's starting here, and I'm going to put a little hole there just to show you that we're not including minus pi, and all the way around to positive pi here. Okay, so argument of z is giving whatever angle we can create for z, okay, or we can think about for z that lies in between negative pi over 2 and pi over 2. So for example, let's say we were looking at the argument of I. Okay, the argument of I, since I is right here, would be pi over 2. Okay, the argument of negative I, okay, wouldn't be 3 pi over 2, it actually would be negative pi over 2. Okay, so let arg of z again denote the unique argument of z that lies in between negative pi and pi. And by the way, why it says unique is if we restrict to these angles alone, then every complex number only has a single angle or argument in this case. Okay. All right. So that's our arg function. Okay. Then we define the principal logarithm as follows. Okay. So the principal log function is defined on c less 0. You still can't plug 0 into the log function, just like you couldn't back in calculus. So the principal log defined on c less 0 to c is defined by, so ln of the absolute value of z, which shouldn't come as any surprise because that's what we just talked about. The real part has to be ln of the absolute value of z plus I times this argument here, where this argument function is what we were just talking about. Okay, so this right here is what we will call the principal logarithm. And I'll put a little note. This is the log that we'll probably mostly be dealing with. With this log. Okay, so let's look at some examples. So again, I'm going to write up here log, the principal log. And by the way, I know it's super subtle, but whenever we're denoting the principal log, we're using capital L-O-G, but notice that it's not fancy L anymore. So usually when we leave off the fancy L, or at least especially if you're reading your book, you're thinking about principal log. Principal. In any case, so the principal log is equal to ln of the absolute value of z plus I times this argument function of z. Okay, so let's say we were computing log of, let's say, 1 plus I. Okay, so first of all, this is going to be equal to ln of the length, or the modulus of 1 plus I, which we'll have to think about in a second, plus I times the argument of 1 plus I. Okay, so let's go ahead and draw 1 plus I. So 1 plus I would be right here, okay, in the complex plane. Okay, so what's the angle that would make with the positive real axis? That would be 45 degrees, or pi over 4. Okay, so this would be ln of the modulus of 1 plus I plus I times pi over 4. And now let's think, what is the length of 1 plus I? Well, this is equal to the square root of 1 squared plus 1 squared. Whoops, ln of this, I should say. I pi over 4. So this is ln of the square root of 2 plus I pi over 4. Boom. So that would be the log, or the principal log, of 1 plus I. Okay. Now, a quick little note with the principal log. Again, this is only one log. Remember, think about the logarithm function as a family of functions. We could have defined the argument instead of minus pi to pi. We could have done 0 to pi, or 0 to 2 pi, I should say, like this. Or we could have done 0 to 2 pi like this. Or we could have been really, really fancy. Maybe we did something like this, like negative pi over 2 to, let's see, I got to get a full rotation, right, to 3 pi over 2. Okay, so there's infinitely many logs. The convention that mathematicians usually go by is this one right here. We usually take it to be between negative pi and pi like this. Okay, but just keep in mind, there's infinitely many logs we could take. There's not just one logarithm function, but generally, though, we are going to be looking at the principal log. So a couple of notes. First note, the principal log is not a branch on c less 0. Remember, we defined a branch as a continuous function from g to c. Okay? Well, the principal log, which can be defined on c less 0, is not actually a branch on c less 0 because it's actually not continuous on the negative real axis. So if I draw our complex plane, so here's the negative real axis, here's the positive real axis. So if we approach from the top, okay, this way, all of the complex numbers, or the arguments of the complex numbers, would be headed towards pi. Okay? However, if we approach it from beneath, all the arguments of the complex numbers here would have an argument approaching negative pi. So our function would not be continuous there. Okay? So the principal log is actually not a branch on c less 0. However, we could make it a branch if we get rid of the negative real axis. So it is a branch, and this is why I was drawing that family tree kind of weird. It is a branch on c less the negative real axis. Negative real axis. Okay, so our principal log, not a branch on its full domain, but if we restrict its full domain to c less the negative real axis, then we don't run into this issue where we have points going to, or at least arguments going to pi and arguments going to negative pi. We get rid of this. And so it's actually a branch on, kind of like what I drew before, on all of c except for the negative real axis here. Okay. Kind of cool. So a couple of notes on the logarithm. So first of all, kind of like what we saw earlier, what we were talking about earlier, any other branch of the logarithm must differ from the principal log by 2 pi I. So remember what we saw was that if you have any, and let me use fancy L here, log of z had to look like ln of the modulus of z plus I times some angle function. Okay. Well, for us, and if we're using the principal log, then this angle function for us is that arg of z, where this angle is coming from negative pi to pi. Okay, but again, you could define another angle function, but at worst, it's just going to be a multiple of 2 pi I off of, or 2 pi in this case, off of argument of z. So any other branch of the logarithm, remember there's infinitely many of them, there's a lot of them, at worst, it looks like our principal log function, but the angle function might be off by some kind of multiple of 2 pi I. And the reason why it's I, it's because of that I right there. And then 2 pi because, well, we're thinking about angles and rotation and all that good stuff. Second thing, logs don't perfectly cancel out with exponential functions, so you have to be careful. We'll see this at the end of the video, but for instance, if you use a different angle function, you might not get this cancellation as cleanly. I'm going to use fancy L there again. I'm going to put here, Okay, but we'll see that at the end of the video. And then now, from now on, if we just say log function, we mean the principal log, unless we say otherwise. Okay. So if you guys remember from the last video when we defined exponential functions and trig functions, a lot of the properties that we had back in calculus or in pre-calculus sort of extended pretty nicely. And we got some new ones, right? Like the exponential functions periodic. With the logarithm functions, it's actually a lot more complicated. And in fact, we don't have the nice product rule that we had back in pre-calculus. Remember, the product rule said if you had log of, let's say, m times n, then this is equal to log of m plus log of n. Unfortunately, this product rule doesn't exist for the principal log. And let me show you why. Or let me give you an example of why. So let's consider log of negative I. And again, remember, we see log by itself in no other context. Think principal log. So log of negative I, well, on its own, without being very clever, this is equal to, by definition, ln of the length of negative I plus I times the argument. Sorry, I had to capitalize that. Argument of negative I. Okay, so let's think about that. So let me draw a negative I here for us. So negative I is right here. Okay, and so the length of negative I, that's 1. Okay, plus I times the argument of negative I. Remember, we're thinking, because it's principal log, negative pi 2 pi. Okay, so the argument of negative I is actually negative pi over 2. Okay, so if we simplify this whole thing, we'll remember ln of 1 is 0. So we get in the end negative I pi over 2. Okay. Now another way we could have calculated this, though, if we think that if we sort of think about it in terms of this quote-unquote product rule, would be the following. So negative I is really negative 1 times I, right? Okay. Well, let's compute log of negative 1 plus log of I. And I'm going to show you that we don't actually get the same thing, so this product rule fails. Okay. Well, log of negative 1 is just, well, ln of the absolute value of negative 1, okay, which again is going to be 0, so nothing too crazy there, times the argument of negative 1, okay, plus the log of I is just natural log absolute value of I, or modulus of I, plus I times the argument of I. Okay. Well, again, here, the absolute value of negative 1 is just 1, like it is in calculus. So we're going to get ln of 1, which is 0, plus I. Now, what's the argument of negative 1? Well, negative 1 is on the negative real axis, right? So the angle for negative 1 would be pi. Okay. So we got these first two terms done. Plus ln, what's the length of I? The length of I, again, is 1. So ln of 1 is 0. Plus I times, what's the argument of I? The argument of I is pi over 2. Okay, because I is living on the positive imaginary axis. Right? So if we simplify this a little bit more, we get I times pi plus I times pi over 2. And so in the end, what we get is I 3 pi over 2. Okay. Now, what do you notice? Did we get the same thing here? And the answer is no, right? Negative I pi over 2 is not the same number as I 3 pi over 2. So unfortunately, we do not have the product rule with our principal log. Okay. However, we do get some nice properties, though it still has a nice derivative. So the derivative of the log function, and actually this is true for any branch of the logarithm, not just the principal log, but the derivative of the log function with respect to z is just 1 over z, just like it is back in calculus. Okay. Now I'm just going to say a proof. If you wanted to prove this, you use the inverse function theorem that we talked about a bunch of weeks ago, or a bunch of videos ago, I should say. Use inverse function theorem. But in any case, the log still has a pretty nice derivative, 1 over z. Okay, so now that we have our complex logarithm function, we can actually talk about complex exponentials. And you might be like, wait, didn't we already talk about complex exponentials? Not quite. So what I mean by a complex exponential is taking a complex number and raising it to another complex number. Like maybe you've asked yourself, how do you do I raised to the ith power? Like what is that? Or what is I plus 2 raised to the 3 minus I? Okay, how do you actually do that? Well, now that we have our exponential function and our log function, we can actually take care of that now. Okay, so given a and b and c, with a not equal to 0, okay, so our base is still not 0, then the principal, and the principal is because we're using the principal log here, the principal value of a to the b is defined as exp of b times log of a. Okay, so for instance, I to the I would be equal to exponential of I times log of I. Okay, and like we just saw earlier, what is log of I? Log of I was I times pi over 2. Yeah. My memory is not too bad yet. So this is going to be exp of I times I pi over 2, which is exp of negative pi over 2, okay, which is equal to just e to the negative pi over 2. Boom. Okay. So this is how we take complex numbers raised to complex numbers. We use our x function that we defined and our principal log as well. Now notice I'm saying the principal value here. And the reason again is because we're using the principal log. If you use another branch of the logarithm function, your complex exponential will look a little bit different. All right, so now that we have our complex exponentials, we can actually define e to the z, which is sort of the analog of e to the x back from calculus. So e to the z is just defined as exp of z times log of e. Boom. So that's how you would actually take e to some complex number. It's exp of z times log of e, where this is our principal log. So if you can think about the way we're defining it right now, this is the principal exponential function e to the z. Now, like I said earlier, remember exponentials and logs don't necessarily cancel out as nicely as they used to in calculus, and let me show you why. So e to the z, like we just defined, is equal to exp of z times log of e. Okay, so hopefully there's no arguments there. That's how we just defined it, right? But remember, we're using the principal log, right? So using the principal log, or the definition of the principal log, that's how we get this, which essentially lets us cancel out and get exp of z. However, if you use a different argument function, not the nice one that we are using with the principal log, no longer are you going to get this really nice cancellation out, okay? So you have to be really, really careful about this. If you don't use the same argument function that we did with the principal log, then your cancellation law might not work out as nicely as you want it. So in this case, we do actually get the cancellation law so that e to the z is exp of z. You might get something else if you use a different quote-unquote angle function, so just be careful.
I told you. You'd die for that.